Convolutional neural network. Convolutional neural network, call it as CNN. So we start with my convolution neural network, and in the convolution neural network, we start by we are starting here with the examples. So yeah, let's see the CNN topic in terms of documentation. Also, we can talk about that. So how exactly the convolution neural network works? Let's break down them theoretically first. Every convolution neural network that you are trying to understand here, this is a supervised, again, it's a kind of your feed forward neural network. It is not back propagation. This is part of your feed forward neural network. Different types of CNN. The types are CNN one dimension, CNN two dimension, CNN three dimension. CNN one dimension is used for a 1D array or CSV files. CNN 2D is used for my images. CNN 3D, this is used by your video analysis, 3D images. These are your three things. Let's talk about the different steps which are involved in CNN. We need to break down them. Steps involved in convolution neural network. Number one, convolution. In convolution method, we just create a convolved matrix or call it as feature matrix. This includes steps like filters, strides, padding. These are all different layers which are used to prepare your image. Kernel matrix, number of filters, strides, padding. These are your sub steps which ultimately prepare your convolved matrix. Going through the filters, kernel matrix, we require strides and padding layer as well. We combine them to prepare our final convolved matrix. Then we have got rectified linear unit that is given by ReLU. Point number 3, flatten, fully connected neural network or FC layer. Fully connected neural network is given by your. Now let's try to understand here what are the different steps. These steps will be prepared how. So let's try to understand it. Let's try to understand here the convolution neural network in depth. Okay. As I was telling you that here in this case, we are having multiple layer. Sorry. These are the steps which are involved. Remember first that your images are made up of zeros and ones. Color matrices are there. So images will be represented as a very big matrix like this. And we need to convert this big matrix into a flattened array data, which is basically an individual array value. Individual elements will be there. These individual values goes through the fully connected neural network to create our multi-class classification. This is my what you will say image matrix, and from these image matrix we basically prepare and individual features. So this particular journey of converting your image matrix to individual features goes through multiple layers of convolution plus ReLU plus pooling. Okay, it will be done 2 times, 3 times, 4 times. Then we will have a flatten array, flatten value, which will convert a matrix, final matrix, into an individual features, and these individual features will go through the dense neural network that we learned just before this. The only difference is that here it will be either softmax or sigmoid, depending upon if you are creating a binary class classification or multi-class classification. The main objective here is to prepare the various steps are involved in this. So let's go through those steps. First step is the convolution layer. Convolution layer. In case of the convolution layer, so in this layer, features of raw input image is extracted. It also reduces. It also reduces the shape of my original image data. So in this features of raw input image is extracted and it also reduces the shape of the original image data. Let's bring out here my shape of the features. As you observe here, this is my grayscale image. Now if you will observe here that we are talking about, that's my grayscale image. If my image is a grayscale image, remember that it will have a dimensionality as 1, and it will have let's say width equals to w and h equals to h is my height. How many boxes are there? 1 2 3 4 5, right? So the shape will be 5 cross 5. Grayscale image.
Its dimension is 1 or 2?
Depth. D is depth, not the dimensionality. Depth. Now this is an grayscale image matrix. This will be multiplied with the kernel matrix. Remember, kernel matrix I have also talked about in OpenCV, and I said that I will explain you that again in sharpness topic, or in blur topic. We have discussed that, where we talked and created a matrix, and I said that this kernel matrix can be of only odd shape. So this is the kernel matrix. Here we are taking even further smaller, which is just 3 cross 3. This is a 3 cross 3 matrix with my filter width and my filter height. Now this particular shape that you observe here is known as your kernel matrix. Let's get the resultant value. Resultant value will be another matrix, and let's say this is your resultant value. Now the resultant input value will be basically resultant of this placed over the center value. Okay. Similarly, this will be placed here, and let me change the color here for your better understanding. How it will be placed? So the center will be placed in the center value of the kernel will be placed as the at the first element. This is how they are placed, and so obviously in that case, this particular portion will be multiplied with this. Then this particular portion will be multiplied with this, and the next one will be multiplied with this. After multiplying it all together, we'll get one single individual value by adding them together, and that added value will be the convolved value or new input. What happened to the shape then? So the shape will be reduced in this way: h minus f of h plus 1. So the resultant height will be reduced to h minus f of h plus 1, and width will be reduced by w minus f of w. So what should be the resultant? 5 minus 3 plus 1, and what will be that? What will be the resultant matrix then? 3 cross 3. So this is your first step. Now here you will observe that we have just introduced the kernel matrix, but how exactly it will go through all the other images part? Will it able to cover it? And if it is able to cover, then how it will exactly work? And what about if my dimensionality, sorry, if my depth of the images are 3? That means we are having an RGB part then. So remember here that what is going on is called as your element by element matrix multiplication. That means every color will get multiplied with only on that portion, and then it will be added. So it will be sum of convolved matrix is calculated by summation of element by element matrix multiplication between input and kernel matrix. Okay, let's pick here my RGB image, red color. We got here my red color, then we have got my green color, and then we need a blue color as well. It's given by RGB, red matrix, green matrix, and blue matrix. So it's a 3D image. Let's fill it with the color. This is how my image will look like. Okay, let's multiply. Now each box will be filled with. Now remember that this is a very big matrix. We have selected here this particular value, but there will be other portions as well which will be alongside this. See that we are having the values here, all these directions, and every position will be filled with color pixel. Let's say this is 10, this is 21. Color can range between 0 to 255, right? 20, 22. This will be, let's say, 20, 23, 27. This will be, let's say, 15, 18, and 19. Okay. Now this will be multiplied with a individual matrix, which is called as your kernel matrix. That's what I said, right? Which will be having a shape of 3 cross 3. This is that small matrix that we are seeing, and the shape of this matrix is 3 cross 3. Shape of the matrix is 3 cross 3. 1, 0, minus 1, minus 1, 1, 0. Let's say minus 1 again. 0, 1, 1. Okay, let us multiply these numbers. 10 multiply with 1, 20 multiply with 0, 25 multiply with minus 1, 22 multiplied with minus 1, 23 multiply with 1, 27 multiply with minus 1, 15 multiply with 0, 18 multiply with 1, and 19 multiply with 1. Get the resultant output. Now remember that these matrices will be not same. The values I'm talking about, shape will be same, but the values will vary. Now remember here that this matrix will be placed over this position. Okay, it will again start from the center value, of course, but it will slowly and steadily will start moving towards the right side. First covering all the rows, and then it will skip one row, and then it will start covering again bottom, and then it will go. I'll show you through the GIF that how exactly it moves. This movement is known as strides. With the help of a stride, which is generally of shape 1 cross 1 or 2 cross 2, it covers all the images, it covers all the pixel value of the images. Now for the first time, when it is working with the red, green, and blue values, the resultant input data should be again one matrix. But how it will be done? Remember here, it is all about the individual value. So here individual value is getting multiplied, as you can see that I have placed here 10 with 1, 20 with 0, this with minus 1, then minus 1, then 1, then minus 1 again, then this is 0, this is 1 and 1. Similarly, it will happen here as well. Now multiply them. Meanwhile, I'm writing multiply these individually and then sum them and give me the resultant output. Now I'll change here some numbers, multiply them individually to get our resultant. Okay, can you give me the output? First value resultant. Sum these value and send the answer in the chat. Minus 4. Okay, let me try. 10 minus 25 minus 22 plus 23 minus 27 plus 18 plus 19. It's coming out to be minus 4. Okay, next. This comes out to be 50, I guess. Second matrix is coming out to be 50. Third matrix, let's assume that this is coming out to be 10. We will add them individually. There is a concept of bias here as well. And bias will be equals to 1. Bias value is equals to 1. 60 minus 4. We got here my 56 value. Similarly, this will continue to create our matrix. That's my convert matrix. That's my convert matrix. Now, During the convert matrix, we need to understand the other further steps, which is the requirement of strides. So as I said, to cover up, like right now, it has positioned itself to take these portion. What about the other portions? To cover up the overall portion, we need to move the kernel over the surface of the input image. That movement is known as a stride. So we'll go through the stride here. Stride is number of pixels. Number of pixels shift over input matrix. Common strides shape are 1 cross 1, 2 cross 2. Kernel matrix that moves 1 pixel over my input shape. We got here my stride. Next, we need to understand the padding. Sometimes the shape of input image and kernel matrix, they does not fit properly. This is my second padding part. Zero padding. There are two type of paddings. First is zero padding. In this case, basically the around the image, zero pad is added, 1 pixel around the images. I'll show you what it means. So adding 1 pixel pad across image shape, padding will be filled with 0. Padding equals to same. Valid padding. This means that there will be no padding here. Why it is required here? Why padding? So remember that sometimes the shape of the image and the kernel will not fit. Remember the kernel matrix is a 3 cross 3 or 5 cross 5 or 7 cross 7. These are the common shapes. This is your kernel, right? Common shapes are 3 cross 3, 5 cross 5, 7 cross 7. The larger will be the size, the that by that margin your image will be reduced. Now we have added all these. When there is no padding, image data does not fit to kernel shape. So if they does not fit, those extra data will be dropped. So it will be dropped. Extra data will be dropped. This is my image. Around the image, this is how my data will look like. What about the zero padding? So zero padding will be the extra matrix. Let's say the extra matrix appear look like this. This is my extra matrix. So we'll add here the extra details is given by something like this. So around here you will have zero padding. Zero padding. Where my kernel matrix will be placed. It will be placed like this. If you are still confused, let me show you a GIF, basically to let you understand what exactly is going on here in convolutional neural network. Just give me a minute. I'm still trying to find out where it is. It's not able to get. Excuse me. Okay, got it. So it will appear like this. Let's say if I'll add here a blank window. So it will appear like this. This is what happening when I explain you the things. This will give you the clarity what happened. There's a kernel channel that has been created. This is your kernel matrix of shape 3 cross 3. The values within this, you can consider it as your weights, your input channels, which is red matrix, green matrix, and blue matrix. It will be multiplied, and this movement. Now you can see that there is a zero padding is also added here. This is your zero padding.
Stride is 1 comma 1 here, right?
Stride here is 1 cross 1, of course. Okay, so that's it. This is all for the day, and now we will go ahead.
One last question, sir. When can we decide the zero padding is required? I mean, size of the image here was say 5 by 5 original, and kernel was 3 by 3. But
Apply zero padding
padding
everywhere. Apply zero padding everywhere.
5 by 5 with 3 by 3 will require padding, or and if
There is no
it could
as
have
such
been.
like requirement or all. I'll say like apply it everywhere because
Oh,
valid padding we don't use. The problem with the valid padding is that we need to drop the image pixels. So why we will drop any image data? Okay, thank you all everyone. We will meet you all tomorrow now to continue this. Activation function to convert negative values from convolved features to zero value. It also add non-linearity. It also add non-linearity characteristics. Also, as I said, it is used in most of your neural network, ReLU is used as a part of your input layer, and reason is just now we discussed that ReLU helps to prevent exponential growth in computation. CNN or even other neural network to compute faster. So hope you have read it. This is one thing about the ReLU that you need to remember, just to give you an idea about what ReLU actually does. Let's say I have the shape like this, 4 cross 4, and it will have some numbers, right? Now the feature calculations can result into, go with my rectified linear unit, and from here we have all my values. Now remember, wherever the negative terminology is there, that will be replaced by 0. Rest all will remain as it is. Only the negative part will go. The negative part will go from here, and positive part will remain as it is. That is what the rectified linear unit does. Part number C, pooling layer. Pooling layer. This is used for reducing dimensionality of convolved matrix, shape. Now we'll have a very large shape of the matrices as well. From there it will be reduced. Let's say I have got the shape of 4 cross 4, and I will apply into this max pooling. Default stride is 2 cross 2, and default max pooling shape is also 2 cross 2. Now what happens if in this case that we will have to take the value which will be like this. So here we go. This is my first matrix of 2 cross 2 which will be selected. This will be the second matrix that will be selected. This will be the third matrix which will be selected, and the fourth value will be like this. It goes all the way till the max pooling, and then according to the shape it will select the 4 values. What all my 4 values here? Those 4 values are max of these 4. So minus, of course this will be 12. Sorry, let's say the negative values like this. Let's eliminate the negative terms. Okay. Now tell me, in this selected region, what is the maximum value? 25. So we have got 25. In this selected value, what is the maximum value? 30. In this, what is the selected value? 19. In this, what is the selected value? 21. And this results into a shape of 2 cross 2. What are the other pooling layers that we could have taken? Max pooling. Similarly, we have got average pooling as well. And similarly, we have got sum pooling as well. So we have got 3 here: max pooling, average pooling, sum pooling. These are my 3 combinations. What in case of 1D this work? What do you mean by that?
I means dimensionality reduction, which we are doing over here. So in CNN 1D will
No, not CNN 1D. It is in 3D. No, sorry, 2D.
this one is in 2D, but in case of 1D, suppose we are taking Excel or CSV sheet, will this pooling will work?
In that case, we have taken 5. Let's say we have
Oh,
taken 5. So 5 selected shape. Out of that, it will select which one is the minimum one. And then
okay.
with a stride of 2, it will again select the next 5, and then again it will find the minimum. So in 1D case, it will be like this. This is how the 1D will look like, right?
Yeah.
So in that case, let's say we will be having some long value, and we'll have our, let's say we have selected stride equals to 5 in that case. So it will select the 5 value, and out of that 5, it will find which is the minimum value. Sorry, which is the maximum value.
And out of that value will be. selected.
will be selected and will go to the next layer.
Dimension will get reduced.
Correct.
Okay, thank you.
Now let's repeat here A, B, and C to perform dimensionality reduction to reduce image shape until we have a very small feature left, very small feature matrix as a final. Let's talk about the part number D, flatten. We have the flatten part, and let's take the shape of the, this is how the input will look like now, and it will have some number. Let's say the selected values are 25, 30, 19 and 21. 25, 30, 19 and 21 are, this is my matrix. Now let's talk about the shapes here. This is how my shapes will now appear. Now it will have different shapes. Let's go ahead with this to reach to the last point, and the last value. Now in between there will be multiple filters, and this number filter will be equals to, like in this case we can say that my number of filter is equals to 64. This number of filter is equals to the 64. Last value we had is 10 in the end. Okay, apply flatten. Now after applying flatten, we'll have the values written here, which will return me 25, 30, 19, 21, and we'll have 10 in the end. This is what in the end we should have. Okay, now remember that this is having a shape of 2 cross 2, and the number of filters that we are assuming is 64. So let's multiply all. That is 2 cross 2 cross 64. This will result me 256 cross 1. So 1 image has generated around 256 features for my final layer, which is called as your dense neural network. This is how it works. And these are my final features, which will go to the, these are all my final features for a dense neural network. After this, we'll have and we'll reach to the part number E, which is known as your fully connected neural network. Fully connected neural network. To that, we will connect all these values, and we will perform the classification. The fully connected neural network is similar to the dense neural network that we created. Simple neural network we will create in the last layer, and this is the layer which will perform the classification majorly.